So,
Yeah, Arun, please go ahead.
yeah. Hello, Udit. Welcome to the workshop. Sorry for keeping you waiting.
Thank you, Arun. That's
Yeah,
totally
and give me the honor of introducing you. So it's our pleasure and honor to have Professor Udit Bhatia with us today for the next talk. Udit Bhatia is an assistant professor in civil engineering at the Indian Institute of Technology, Gandhinagar. And his research interests include the recovery and resilience of network systems, uncertainty assessment in hydroclimate extremes, and physics-guided data science. Udit received his PhD in interdisciplinary engineering from Northeastern University at Boston, USA, and his research has been highlighted by national and international media and publications including Science Daily, AAAS, Eureka Alert, R&D Magazine, Yahoo, and Big Data Journal. He is also co-author of the book Critical Infrastructures, Resilience, Policy and Engineering Perspectives, published by Taylor and Francis. His work in applied network science, infrastructure resilience, and extreme value analysis is currently being used by policymakers at various levels. His work has contributed substantially and directly towards publications in disciplinary and interdisciplinary venues, UNA UK report, encyclopedia articles, peer-reviewed book chapters, award-winning conference papers, and US patent in his name. And personally, I also collaborate with Udit, and I've known him to be an excellent researcher. So welcome, Udit. And
Thank you.
The floor is all yours.
Thanks a lot, Arun, for this kind introduction, and welcome everyone for this late evening talk. So I would be talking about robustness and recovery of built and natural systems subject to hydro-meteorological extremes and how we have been integrating data, dynamics, and complexity to address a few topical problems that our current world faces. Now you might be tired waiting for dinner. So before we go ahead, here is some trivia for you. So you can see 4 pictures on the screen and please feel free to use a chat window as appropriate. Can you tell me what are the similarities and differences in these 4 images? It's not very difficult question, but may wake you up as we go for late evening session. So I'll wait for 5 more seconds. Anybody who can tell me what are similarity and differences?
See water everywhere. And see water everywhere. Extreme amount of water.
Absolutely. And water everywhere. And difference is that all these pictures, they are taken from 4 different corners of this world. So few coming from developing nations, few coming from developed nations. So when we talk about hydrometeorological extremes, it's no longer a problem of developing versus developed world, whatever we may call first world country, third world country, second world country, but it is a universal problem now, given the exposure and vulnerability we have, and with intensification in hazards, regions across the globe, they are facing that repeated and intensified magnitudes of risks coming from these kind of events. So here you would see a couple of pictures from the US, one from Thailand, of course, one from India, and both in urban setting as well as rural setting. And this is the last trivia for the day, I promise. Again, the question remains the same, but picture changes. Can you spot the similarity and differences? In last picture, we saw that finding similarity was easier. It was water everywhere. Here, finding difference is easier. We have 2 pictures of droughts, 2 pictures of floods. But what is the similarity here? Of course, both are related to water. But what else? Again, I will wait for 7 seconds before I answer the question myself.
Yeah, so one, there's an answer in the chat window. Extreme climate conditions.
Yeah. Extreme climate conditions, definitely the similarity. All these 4 images, they come from the same city. They come from the same region surrounding the city. And can you guess the city? So all these four images are taken in and around Chennai at different points. So that means that it is not only one kind of hydrometeorological hazards that are going to bother us or are already bothering us, are already making our infrastructure systems crippled, are impacting our interconnected lifelines, are being the primary cause of disruptions to ecological services, but we have to be mindful of the extremes on both sides. But what does that mean in the context of planning, policy making, designing, and just like we talk about sustainability, resilience has become one of the keywords that engineers, policymakers, they keep on talking about. For example, there was a call from United Nations that we need to shift from risk to resilience. It's great to know that what is the magnitude of risk that our infrastructure systems are going to face in climate change, in changing climate, but it is just not enough. Then there was call from academicians. So if you see, there was a perspective or a brief commentary from the then editor-in-chief of the Science, where Marcia McNutt highlighted that our communities need to be thinking beyond seawalls for future floods and hurricane protection. And that essentially calls for changing the resilience paradigm. But when we think about translating all these ideas, policies, we face multitudes of challenges because the way resilience has been defined, there are more than 70 ways to show resilience. As one of the correspondences in Nature highlighted a few years back, that if we go with different definitions of resilience, the outcomes can be totally different. So we have to be very mindful of the definitions that we talk about whenever we are trying to quantify resilience, embed resilience into our system. And finally, what World Economic Forum does every year is that they try to identify the events which have high likelihood and high impact. So if you see the top right corner, the first one, which is on with the event with high likelihood and high impact, comes out to be extreme weather event, followed by natural disasters, then failure of climate change mitigation and adaptation. So in summary, we are facing this challenge not only from droughts, not only from flood perspective, but this entire magnification of risk becomes a multifaceted challenge. And when we try to address the embedding of resilience into our systems, we have to understand the underlying complexity, underlying dynamics, and that is where data is most helpful when it comes to understanding these systems. Now, before I go into the core case studies, I would like to discuss that how we are interconnected, what appears to be failure of a man-made system or network system find their root in some of the naturally triggered event. And one of the classic example is power blackout of 2012. So what happened in 2012? We had delayed monsoons and heat waves in month of June and July of 2012 across India. At the same time, water demand was high because in many states it's the peak kharif season where farmers would be planting rice or paddy crops where water demand would be high, and all these events culminated into increased stress on power grids. And somewhere between Bina and Jhansi on 30th of July of 2012, there was a localized power failure. But by virtue of the interconnectance of our grid, by the evening of 30th of July, around 50% states in India lost the power. By the evening of 31st July, the secondary impacts or cascading impacts started surfacing. And we observed that the failure that started with failure of two local points on grid somewhere resulted in bringing transportation systems to halt. Many trains were stranded, industrial activities were stopped. And that is what we say is that the virtue of interconnectedness became the curse of connectivity. Not only at global scales, these events are also gaining predominance at regional scale. All of us are familiar with Kerala of 2018, that deluge of the precipitation deluge that happened during monsoon seasons of 2018 was recorded as 1 in 100 year event and in fact, on certain days, even higher accidents probabilities were noted with those extreme precipitation. And what it resulted in that of course, the certain parts, low-lying areas of Periyar Basin, they got flooded, but it didn't stop there. These saturation in various zones of soil resulted in ideal condition for landslides and debris flow to get triggered. And over a couple of months, from all the way from 1st July to 31st of August, we saw many events unfolding both in space and time. That means the flood grew, the number of areas that were hit by landslides and debris flow increased dramatically. And it, of course, resulted in disruption of lives, economics, and disruption to transportation sector, power sector, and all the lifelines that we crucially depend on for our day-to-day operations. And this is one of the recent work about which I will talk in more detail. So that all these problems, and as a solution person, given that I work in area of resilience, try to quantify various aspects, we thought what would be the best set of tools, best set of techniques to look into these system of systems. And then, as the name suggests, given the interconnectivity that we are dealing with, we could not think of anything better than using a network lens to look all these systems into an integrated manner. So for example, here I present this 4-tier diagram with climate/weather systems on the top. The advancement of understanding help us prepare for both short-term disaster management and long-term adaptation goals, as well as setting mitigations goals at city and regional scale. Once we have better understanding of these hazards, propagation of these hazards, interconnectivity, that what we also call as teleconnections that persist in these extreme events over longer duration as well as longer extents of space, how they interact with our network multiplex of built systems and social networks become crucial. And once we understand these complexities or layers of complexity, it ultimately help us come up with an informed strategies for resilience, understanding how our cities should recover once they are devastated by floods, droughts, or compounding events, as I discussed in case of Kerala flood. And we then try to conceptualize this multi-level framework, that what it would translate to when we start looking into regional hazards, such as the one we had in Kerala. That is, we had extreme precipitation induced hazards, including precipitation extreme itself, flooding, landslide, debris flow, and how they ultimately disrupt the day-to-day life of people through the connectivity losses, which ultimately impact the socio-economic health of these particular regions. And finally, what we realized that when we look into the resilience and robustness characteristics, as we also learned in the previous wonderful talk, that how we learn lessons from ecology and apply to other domains to understand evolution, generalizable patterns, we took an inverse approach. That is, the lessons that we are learning about recovery of built systems, restoration of built systems, can we also generalize those lessons to the natural systems? Can we use the recovery lessons that we have learned for power distribution system or Indian Railways to understand how to cope up with the sixth extinction? So there is an excellent book by Elizabeth Colbert which talks about that the sixth extinction that is imposed by Anthropocene. And recently I was reading an article that United Nations declared next decade as the decade on ecosystem restoration, with an idea that how we can restore most critical ecosystems to their pristine state by end of the decade. So adding this all up, again, we realize that ecosystems are complex systems. We have moved beyond two species model where we have hundreds and thousands of species interacting. Again, we find that a network lens to understand these efficient restoration strategies for ecosystems can be of great help to design something actionable for policymakers, for stakeholders, for ecosystem managers, as well as for engineers and scientists. So I will illustrate these broad points that I have discussed so far through three case studies. That is the work that we have done on these three layers in our lab. We are very young lab, still experimenting with a lot of things. So I will try to give the glimpse of what we have been able to achieve in last few years, I would say, and in last couple of years, I must say, and what it means for the future direction, not only of the lab but in general for us to progress as a community. So in first case study, I would be talking about some theoretical exercise that we did. That is, can we generalize some of the destruction methods that we have learned on networks to understand the early warning and tipping points in networked infrastructures, which are now subjected to concurrent and repeated disruptions. In second case study, I would be talking about how we really model these extreme precipitation induced concurrent events using various dynamical equations, which help us understand spatio-temporal characteristics, mechanism of propagation of various hazards, and ultimately give us a way to realistically look into disruptions that are network space. And finally, I would discuss some of the work that we have done in the area of universal and generalizable restoration strategies for degraded ecosystems, and demonstrating its application on 32 ecosystems across the globe. So before I go to study one, here is the prologue. During my PhD time, this was actually one of the lines of work that I started, where I wanted to understand that the left side of robustness is fairly well understood, fairly well documented in network science literature. That is, when systems are subject to targeted attack or they are subjected to random failures, and if they exhibit certain patterns in their degree distribution, we often see that they are fairly robust. So specifically when they exhibit power law in their degree distribution, it is well established that they are fairly robust to random failures, but targeted failures, that is removing attributes by number of connections or by importance of location, it would hardly take fraction of node removal to bring entire system to its knees. But what was less known is that what if these systems are down? How we are going to respond to them? How we should restore them? So some theories just assume that we can have a mirror-like bouncing back characteristics of this system, or it was simply discussed anecdotally with toy networks, with idealized systems and so on. So we took this challenge and we decided that let us start looking into some real world systems, and when both real world or simulated disruptions impact these systems, can we really use the suite of optimization based approaches and network heuristics to understand, if we follow strategy A versus strategy B and so on, what are the marginal gains that we are going to get in terms of recovery? And what we realize that these network informed strategies can help us rebound with an efficiency of about 230% or 2.3 times more than what a random restoration strategy would do. And then we try to understand that what it would mean in the context of specific hazards, for example, 2004 tsunami, 2012 power blackout about which I spoke, and of course the cyber physical attack, which is highly unlikely, but if it happens, has potential to result in instant collapse of the communication system and hence transportation systems. Then there was again an interesting perspective in Nature where author said that given that the kind of things that exist in the area of understanding robustness of the system, the destruction or strategies to disrupt the network has been perfected. And we need to go beyond just disruption and look into what it means for recovery and resilience characteristics. And by the way, the definition of resilience I'm using in this system is that how these systems go down. But once they are down, what is the best way to help them rebound to their intended state of functionality? And this state of functionality can be measured in terms of functionality loss, in terms of how many people are being served before and after hazard and after recovery and so on. But what was missing in this entire picture is that most of the times the hazards that we are talking about, they are going to sweep a broader area. They are going to impact multiple attributes within the network. So we did not understand what would happen to real world systems like Indian Railways or US National Airspace when these systems are disrupted concurrently and repeatedly, as we saw in case of Kerala floods, where system was under attack, although from the natural hazards, but repeatedly from 1st of July of 2018 till 31st of August of 2018. So we decided, looking into some very simplistic network models, that is how these can we use these network constructs to understand where we would be able to identify some warning regions, and what is the demarcation between warning region and tipping region. Lot of attention has gone to identification and delineation of tipping regions, that is what is the sudden onset of collapse. So the question that we wanted to ask is that by looking into the trajectory of change of functionality, is it even possible for us to delineate some warning zone, albeit small, albeit narrow, but is there some indicator? And in this particular work, we looked into various first order, second order changes in the trajectory of functionality to identify that where are the possible warning regions that could exist in these systems whenever these systems are under attack. I will not go into the mathematical details of that. I, of course, shared the archive link if somebody is interested to refer to the detailed mathematical formulation, theoretical guarantees. But the key takeaway from this discussion that we are observing here is that not only we were able to identify these sudden spikes in some higher order functionality losses whenever we see the onset of warning regions all the way to tipping regions, we also see the generalizable patterns that we get to observe between the robustness characteristics and attack size. So here what we did is that we had two real world systems on which we have been doing a lot of experiments, for which we mined the data from all the open sources, e-ticketing websites that also have the train schedules when you go to book your tickets, and from federal agencies in the US, where they wanted us to understand what Boston snowstorm events like events would mean for their systems. And what we were able to do is that identify the generalizable patterns that given particular attack size, that is if nodes are removed in bunch of 2, 4, 8, 16, 32, 64 and so on, is there some pattern of decay that we observe? And we see that on log scale a, a very neat linear pattern is observed where we get to see that tipping point has been set, and wherever we are observing the batch sizes when these real world systems are subject to the real world disruptions which are happening concurrently and repeatedly. Now, this is what we try to do theoretically is helpful to decode some of the natural or real world disruptions that happen on the system. While in previous studies, our underlying systems were real, the disruptions were all hypothetical. That is, we were manually controlling the batch size just to understand what generalizable patterns we would observe. But we know that real world system is not that fair. Whatever generalizable patterns we would observe on strictly controlled theoretical data may not generalize when these events they knock on our door. So for example, similar kind of concurrent disruptions happened on our real world systems during 2018 flood of Kerala. And as I mentioned that some precipitation events happening during 1st of July till 15th of August resulted in massive disruptions in large part of Kerala, which triggered shallow landslides, flooding, debris flow, and finally infrastructure disruptions. Again, these are the images that have been taken from Periyar Basin, that what was the condition of roads, what was the city of what was the situation of low-lying areas, specifically near the coastline, and what was the associated damage cost. So it was estimated that rebuilding would take around 18 months and cost would be upward of 5,000 crore. But more than that, what becomes crucial is, first of all, understanding that how realistic our damages are. Once damages are realistic, how we design the optimal restoration and recovery strategy. But here challenges were manifold for us. We only had data or information about the precipitation extremes. The flood maps are either not preserved or they are not shared in public. Same is the case with debris flow and landslide. And we hypothesize is that if we are going to look into one hazard at a time, we are going to underestimate the disruption that these events often cause on our system manifolds. And what is that manifold? That's what we wanted to determine through this exercise. So to do that, we again, I would not overwhelm you with all the complexities here, but the key takeaway from this particular flowchart is that we decided that can we look into realistic modeling of hazards, that is floods, landslides, debris flow, by using domain knowledge, well-established models, or even designing our own models, as well as our understanding of network topology, resilience characteristics, and try to understand what could have really happened in these basins when they are battered by hydro-meteorological extremes, including precipitation extremes. And here and when we started doing this exercise, we realized that we do not have any station-based flood data. So one of my PhD students, Raviraj, what he did, he set up his own flood model, a two-dimensional hydrodynamic model that gives us spatiotemporal variation of flood at basin scale using well-established equations. And then he would look into the parameters of these equations and try to do the grid search by looking into the remote sensing products that we get from various satellites, including SAR products, and that is SAR images that give us the flood extents. And then we try to reconstruct that what could have happened in this basin at daily scale. Similarly, one of my postdocs and who is expert in understanding the geotechnical aspects of basins after extreme precipitation events, decided to look into the time series variations in stability of slopes that ultimately tell us how these particular slopes are going to be stable with respect to time. Anything above 1 is considered stable, anything below 1 is considered unstable. And he designs and sets up his own model at where he would be able to determine the factor of safety that each pixel on map would exhibit. And what we observed is that there is a strong correlation between factor of safeties going down below 1 and the events of extreme precipitation, which makes sense if we also look into the triggering mechanisms of landslides when soil get saturated and the effective cohesion becomes less than the apparent cohesion, resulting in triggering of these events of failure. And ultimately, when these landslides happen, they just don't happen in a binary mode. That is, either there is a failure or there is no failure. They are often associated with the continuous flow of heavy matter, including rocks, debris, boulder. And then we try to set up our debris flow model to understand what is the rate of erosion. Now, this gives us good understanding of the three hazards, how flood was triggered because of that precipitation extreme, how combination of flood and precipitation extreme triggered landslide, and how combination of these three events resulted in debris flow. But what we were really excited to understand is that what it means for the road networks in that particular area. And again, we realized that network science lens would be the best one if we really want to understand these interconnectivities and interdependencies that exist in the basin because of these transportation systems. And then we set up our own damage model, try to understand the variation in the connectivity patterns on the system, and try to quantify that how functionality loss would happen. So these are some of the spatial characteristics that we observed, that how our model was performing, how our satellite desert flood extent was, what was the satellite derived flood extent, and what is the difference between our estimates and what we observed from satellites, both for validation period. And finally, for shallow landslide and debris flow, in absence of any real world observations, we rely on metadata where we try to match the pixel location that what our model is predicting and where it was actually predicted that this event happened at what location. So now once we had this understanding, we tried to disperse this information that we had in time over space. That is, for each day throughout July and August, we tried to understand that how floods and landslides propagated for those 60 days in that particular basin. And based on that, we tried to understand that how they are going to interact with the underlying road network. Now, a couple of very interesting non-intuitive things came out for us. If we look into the population distribution of Periyar Basin, we would see that high density of population is concentrated around coastal areas, and factors are numerous. It's a relatively flat terrain. There are a lot of opportunities for communities of all sizes to flourish, thrive here. And the part which is in center of the basin is fairly less populated. It's a highly uneven terrain. Lot of mountains are here. And when we try to look into functionality losses, we realize that yes, flooding resulted in around 20% losses almost instantly. And this water never receded for those 2 months. That is, whatever roads were damaged during that period, that damage persisted for at least 2 months. But what we were expecting is that, given that this is an area with high density of population and high density of infrastructures that may be located here, the functionality losses were tolerable. Uh, Again, the definition of tolerable would depend from stakeholder to stakeholder, but we did not observe any drastic loss of functionality throughout these 2 months. But what really caught our attention is that what happened in August, we observed two major landslide events that happened somewhere in these least densely populated parts, which resulted in the maximum destruction. And then we tried to backtrack that what actually happened, that why we are observing such a dip here. We observed that almost all the most important nodes and segments of these road transportation systems that bind this entire basin together, they are either passing through the highly susceptible zones of landslides or debris flow, which made this entire part secluded of rest of the basin. As a result of which, we lost the major component of functionality because of these triggering events, and the artifact that we have high concentration of most important nodes and edges in one single area of the basin, which gives us a very interesting picture that how we can really inform designing and policy aspects using these fairly uh, convoluted spatio-temporal models to understand hazards and try to give picture for designing of these systems. So now this brings me to, of course, I would be more than happy to share detailed manuscripts of these works. So I'm not going too much into technical details, but idea of this particular talk is to give the kind of things that we have been trying to do in the engineering space using tools that have been primarily developed by nonlinear dynamics groups and physicists across the globe. Then coming to study 3, where we are looking into understanding the recovery characteristics of ecological systems. Now, there has been a lot of interest in specifically network science community to map the universal patterns, understand what are the generalizable patterns that we would be able to observe in systems of different complexities in terms of their robustness characteristics. So the two key studies I would like to highlight here is one by Jiangxi Gao, who is good friend and collaborator, is to understand the resilience patterns in complex networks, which was published in Nature in 2016, where they claim that using some one-dimensional approximations for these n-dimensional system, they can really identify the desirable and non-desirable state without getting into the overtly complex parameter visualization, parameter calibration, but they just tell us that how we can relate the dynamical properties or stability aspects of the system to the network topology. Then another work that came in Proceedings of National Academy of Science 2 years later challenged the notion that one-dimensional projections are great. They give us interesting starting point to simplify these systems, but in some cases they may result in oversimplification. So we need some optimal dimensionality of these systems. And then they try to understand that how the deviations from 1D to 2D model would result in difference in insights and so on. And all these studies essentially use the bipartite networks, which are essentially consisting of plants and pollinators. And then if you have 1,000 plants and same number of pollinators, you would be essentially dealing with 2,000 dynamical equations which are coupled through each other, resulting in explosion of parameter space. And essentially both these studies highlighted that yes, there is need to reduce the dimensionality. There is need to identify some effective controlling parameters that would help us understand resilience of these systems. It can be 1D, it could be 2D, or as the system or the interacting components in the system increase, we may have to go with optimal end dimension, which not necessarily may not be one-dimensional or two-dimensional. But again, what we identified was missing from this area is that what it has for policymakers, what it has for an ecosystem manager, what it has for United Nations restoration decade. So we try to understand that can we really try to understand, try to map these universal patterns that we have observed in context of stability or desirable and non-desirable states to the recovery characteristics of the system. So for this work, we identified 32 ecosystems across the globe for which we have data from various open sourced and metadata repositories. And then we tried to look into various recovery sequences, various extents of perturbation, that what if we take a real world ecosystems and try to identify 20% removal of nodes or interaction in certain patterns. That is, if generalist species who would have many connections in an ecosystem are removed. Specialist species which have very specific ecosystem services and also depend on very small subset to thrive in an ecosystem. What if they are removed in certain targeted fashion? How these network strategies are can give us an information that how the three characteristics, that is abundance, persistence, and settling time of these systems are going to vary when we follow strategy A versus strategy B, which are informed either by ecological properties or by network properties. But what is the near optimal restoration strategy so that we end up with a faster and more efficient recovery? And then we try to understand that what are the different pictures these one-dimensional and two-dimensional models portray. What we realize is that while we observe a consensus between average persistence, that is how many species would be able to thrive once systems reach their equilibrium from 1D as well as two-dimensional models, the results that we observe both from one-dimensional and two-dimensional constructs for the abundance and settling time, they are disparate. They vary. They have large variations when we look into their statistical attributes as well as the most efficient restoration strategies, highlighting that we need to be careful before we go into these high order reductions and come up with field practical restoration strategies. Again, I would not go into the details, but here, I mean, those who are familiar with this world of nonlinear dynamics, they would recognize these mutualistic interaction equations very well. But essentially, we try to identify the optimal, the stable and unstable solution points for both one-dimensional and two-dimensional systems for all 32 ecosystems at each and every time step, and try to identify the winning strategy out of it. Now, this brings me to end of the talk because I wanted to have at least 10-15 minutes to take questions and have discussion with the participants. Is that what's next, where we should head towards now, what it means for the community? So recently, IPCC came up with its physical science, the assessment report 6, which has various components, including physical science basis as one of them. What we feel is that there has been a vicious circle of policy myopia, outdated best practices that we have used, engineering stagnation, and this climate aware engineering and of built and natural systems can really help us transform this vicious circle into virtuous circle, where we use all these dynamics, complexity, data toolboxes that are available to have informed decisions for improved guidelines, for novel engineering and planned interventions to see a better world. So this particular figure is taken from the textbook that Arun also mentioned in my introduction. And one of the things that we were able to do is for the stakeholders, that is New York MTA, is to translate that how we can really go away from suboptimal strategies and design, if not optimal, but near optimal or at least informed restoration strategies after major events like Hurricane Sandy. So in this particular animation, what we did is that we compared what New York MTA actually did after Hurricane Sandy restoration and what our algorithm was suggesting, and tried to map the additional costs that we would incur in algorithm A versus algorithm B. And what we realized that even simple tweaking in our restoration sequences could have saved us an additional $58 million in terms of additional revenue that we could have generated during the restoration process. With this, I come to end of this presentation. I'm really thankful to my young collaborators, Shiva, who does the landslide and debris modeling in my lab and who would be joining as assistant professor at IIT Roorkee next month. Raviraj, my PhD student, who has been doing a lot of work on understanding spatiotemporal dynamics of hazard and relating it to underlying network systems. Sarth, who has been spearheading the work on ecological restoration, which in fact was this entire work was his master thesis, and Utkarsh, an undergraduate student who was leading the study one, where we were trying to understand the theoretical nature of concurrent disruptions on our systems. With that, I end my presentation, and you can always write to me on my email, bhatia.u@iitgn.ac.in, in case you have any interest or any further question. With that, I end my talk. Thank you. Hi, Arun. Can you hear me?
Arun, are you there? While we are waiting to hear from him, can we take the questions, Udit?
Yeah, certainly, please.
Thank you so much for this very nice talk. So I see there are some raised hands, so I'll just unmute them so that they can ask directly.
Certainly.
Yeah, Sunitra, I can take it over.
Yeah, please, Arun.
Yeah, sorry.
You disappear. Please take it.
No, I was just a bit away. Something urgent. Okay, so first of all, thanks, Udit, for the wonderful talk. You took all the way from biology in the previous ecology in the previous talk to landslides, extreme events. So I think we have raised hand from Ayapadas. Please go ahead, Ayapadas.
Dr. Bhatia, it was a very interesting talk, and as someone who is from Kerala and was closely following the flood situation, one comment, actually there is this precipitation data from I believe 1910 or somewhere around till 1970 is there in some format. I was able to download it, but again that getting the land coordinates was a little bit difficult over there. That's just a comment. Maybe you have already got it, but from 70s it was difficult. Let me come to the question. The question is that just in the context of Kerala alone, I'm sure you must be aware that the current Kochi port itself was formed out of an event that happened in 1300 during a massive flood in which the Periyar River shifted its course. And then the new Cochin harbor formed. The earlier harbor was somewhat different. And a similar flood event happened in, I believe, 1930s. Even my great grandmother used to say about this. So flood is huge, massive flood is not an alien thing to that region. Can we, have you thought about anything like, right now we are discussing about what is the current kind of strategies which are possible, but there have been some kind of historical strategies which have been done, probably time lagged over a huge period of time. If it can be mapped, won't it give a better picture of what better strategies could be constructed, maybe in a futuristic manner? Not exactly all strategies of that nature are going to work. I was just wondering because the human race in itself are not alien to such kind of extreme events. So maybe a little bit of modeling, network modeling from history in itself might throw some light. If you have any thoughts on that, it would be great. Thanks.
Thank you. This is great question, Ayapadas. So yes, talking about first of all your comment. Indeed, we have data from Indian Meteorological Department. In fact, all the way from 1901 till yesterday. So IMD maintains this gridded data stream that it shares with researchers who have procured the license. Of course, there are a lot of uncertainties, especially when in 1901 till 1950, then where gauges were limited. So we often validate and cross-validate these data products to understand systematic biases they may have before we use them for our flood modeling, because our entire engine of flood hydrodynamic modeling, landslide modeling critically depends on the accurate estimates of precipitation. Then secondly, talking about reconstruction, I think this is a very interesting idea. Not that it's something that we have tried in our lab. We have not tried this in our lab, but what we were actually trying to investigate in Kerala is that yes, flooding is not new, as you rightly said, to this system. But what about the other associated events like debris flow, landslides, and one of the typical characteristics that we have seen in Periyar River Basin is gradually shifting centroid of population densities towards the east side of the basin, which results in massive deforestation, changes in slope stability characteristics. So we were also interested that, okay, flood is fine. Flood has happened before in this particular area. This is low-lying area and it's a signature manifestations for any flood event to propel. But what it would mean for secondary disruptions, and that's where we wanted to focus a bit more on other concurrent yet related hazards. But I think it would be a great exercise to think about that how we can account for the well-informed interventions that account for the historical development of basin in near past. I would say that anything happening in last 50 or 70 years would be near past, and it may be possible for us to get some meaningful data to do that. But I think this is something worth giving a thought to.
Yeah, thank you, Udit. So we have another question from Satyam. Satyam, please go ahead.
Yeah, thank you. Thanks, Arun. Thanks, Udit, for this excellent talk. I enjoyed it a lot. So I have couple of points to understand. Can you? I think it was probably in slide number 11, most likely. So where you show that the transitions from the green to red and there's a yellow patch. Yeah. So this one in that figure B, so how are you setting this up? Just by checking it visually, or is there a statistical way to say that this is the kind of the phase red, this is the green phase, and this is the yellow phase?
No, so Satyam, I think that's an excellent point. So initially, when we talk about very large systems, it becomes very difficult for us to delineate anything visually. So we were actually looking into the transition points in slopes, that is rate of change of functionality with respect to time. And wherever we would observe the first signal of drastic change, we would call that as the potential onset of warning. And then when we observe the second onset of that trigger again, we call that as the beginning of the tipping point. So again, in the manuscript that I have shared, we have discussed this statistical approach that we have used to delineate these warning regions and tipping regions. I have shown this here on the normal scales, but when we do this entire exercise on log scale and then and try to understand the deviations in slopes, that is where we were able to come up with the analytical solution that how we can delineate these two regions and so on. So
Okay, so there is a like a kind of a statistical as well as like an analytical, I mean, kind of I mean approach to this, right? It's not just by seeing the picture. Yeah. Okay. So that
no.
yeah.
In fact, when we just see these plots, we cannot see anything. But when we do
Yeah,
certain
the
transformations,
one on the left hand, the right hand side, it's very hard. But on the one on the one you saw on the left hand side, right? The figure B, it's quite
yeah,
obvious, like by the guide to the eye kind of argument.
yeah,
That there's a sudden jump, and probably we can say this is the kind of a step, like the phase where you jump from one state to the other. So
yes.
but when
So
the one with which you do the UR end as well as the USA, so I had this kind of confusion that how you are doing that. So there is actually a statistical way and kind of an analytical way to kind of prove your point. Okay.
yes,
Okay,
absolutely.
that's
And even in our manuscript, we show that when we do it analytically, we are able to do this prediction very well for certain kind of networks. But for US National Airspace, we were not. There was a significant difference between what our analytical solution was saying and what we were observing from our experimental methodology. And then we tried to do some mechanistic explanation that why this is happening. But of course, for control systems like BA networks or for Ardoshreni networks, we would be able to see a significant agreement between what we are observing by measuring changes in slope and what our analytical approach is suggesting about these onset of warning regions and tipping points.
I see. So just as a like a kind of, I mean, from your answer, I just had this thing because you talked about the Ardos Reni. So are you kind of like say rewiring the networks as well from the observed one and doing some kind of a null model to see those spikes?
So
Or
the way we, yeah, I think that's exactly what we try to do. What we try to do is that we take the real world system and we observe its property, that is network density or probability of connectance, and then we rewire our Ardoshreni systems, keeping those number of nodes and other attributes same. So the generative attributes are coming from a real world information, but of course rewiring is random to generate our null model. And then the same exercise we do for US National Airspace to generate our null models and then try to understand what are the deviations.
okay, that's great. So, and the other point, I think I don't remember the slide, but it was like when you showing the South India, the road map and the flood map kind of a thing. I think probably slide 15 or 16. I'm not too. I think the next one, next. Yeah, these ones. So these maps are from OpenStreetMap,
Yeah.
or like.
So background maps are OpenStreetMaps, and these road networks actually. So the problem that happens is that when we take data directly from OpenStreetMaps, these nodes and edges would appear to be disconnected. So
Yes.
we spent a lot of time, in fact, couple of months just to clean these data sets so that we get a fully connected network to run our algorithms on. But
Okay.
underlying data actually comes from OpenStreetMaps.
Yeah. Okay. So here, what I'm kind of curious to know that you have the flood network. So the purple one is the road, right? For the flood, landslides, and the debris flows. The boundary is the road, is it? Or like what is that?
No, so boundary is the natural watershed. So since we are setting up our hydrological and hydraulic model, we have to identify the watershed. So this is the boundary of a watershed. That means any precipitation that is falling within purple boundary would not go out of that basin because of its terrain.
Okay.
So we
Okay.
use the digital elevation maps to delineate the watersheds actually. So
Okay.
they
So
do
it's
not
the
represent anything, but Yeah, so they're an abstract quantity that we would not be able to see, but you think of this as boundary of a cup or a saucer, that anything that is
Right.
falling over
Yeah.
the saucer will remain in the saucer, but these are not roads.
Okay. No, that's yeah. Okay. So now it's clear. So what are the blue ones then? That's some blue ones, green ones, and the jungle green ones. The points.
So
So
blue
these are the flood zone.
yes. So blue one is only flood zone. If you see that these are the, so if I show it in little bit of a zoomed version, so this is what blue ones are. When I zoom these
Okay.
blue ones, this is the aerial extent of flooding on a given day. If
Mhm.
you see is something that are running as nerves, this is actually the main river, and around that we see the flooding. So
Okay.
this is what our model predicted, and this pink one is something that we observed from the satellite on the same day. And then we
Right.
quantify how many pixels would be inundated because of this flooding and so on, and then look into the statistics of agreement and disagreement between models and observations, as we would typically do in F1 score, F2 score, and so on. Then here,
Okay.
these green triangles, they represent the location where landslide actually happened in the basin. So we have this
Mm.
data from metadata, and then we try to set up our time series model to simulate the landslide exactly on those pixels. So if you see here, we have around 600 points, each line representing one pixel here. And you would see that for certain pixels, we never had a landslide, which would represent all non-green pixels. Anything which is below one would represent those pixels where we actually had a landslide event. Similarly, for this yellowish color, what we have here is where we had the debris flow after landslides. So debris flow is a little bit different from a landslide, is that even if factor of safety is 1, if your mass is not loose, that volume is not going to come and obstruct the road. But it may still cause temporary damages by obstructing traffic flow for that day because of safety hazard and so on. So this is what the map represents. And we generate these maps for 60 days in continuum. For each day, we will have one map, and then try to understand how these spatial extents of these damages are varying to get this functionality losses and so on. Then another
Okay.
interesting point is that since I am a civil engineer, I would understand to some level that how these events impact our infrastructure. We assume that flood water will recede after one day if same water is not coming next day. But debris flow and landslides, they are going to stay there at least until recovery has happened. And that help us design these network robustness curves by accounting for the restoration time that each event will have with it.
Okay. So can you so from here this picture, I had this thought that in social networks, we have this idea of exponential this thing is the ARGAM, the exponential random graph model. So in that, you can actually use one network to predict the another network. Okay, provided the network size is, essentially the same. Okay, so let's say you have an example is the kind of the Florentine like the marriage and the business network. So whether you can use the business network to predict the marriage network. Okay, so I think here you can kind of think of a similar way, although I'm not too sure how you would do that, because you see, like, spatially the flood is located towards, I think, the Arabian Sea, and like the landslides are far more eastern in terms of
Yeah.
spacing, like spatial, right? But the debris flow and the landslides are more or less, they are in the same places they're occurring. So I think you can
Yes.
kind of think of an exponential random graph kind of approach to to use the landslide network. You can create a network in some way and predict the debris flow, or the vice
Yeah.
versa, the other way. So that would be kind of an interesting thing in which you can kind of think of a new idea from here.
Yeah, certainly. I think that is something we should look into. I mean, I'm not familiar with the exponential random graph generation, but I will
Yeah.
definitely look into that. Thank you. Yeah.
Okay. No
Thanks a
problem.
lot.
Yeah. Okay. Yeah. Thanks a lot. Okay. Thank you.
Thank you, Udit. So participants can also ask questions by typing in the chat window. So in the meanwhile, Udit, I myself had a couple of questions.
Sure, certainly.
Can I
Please.
ask? Yeah.
Certainly.
So
Certainly.
yeah, on the slide that you are, so you have this state of critical functionality, right?
Uh-huh.
What is the mathematical calculation that goes into it?
So, Arun, it's essentially larger size of the largest connected cluster in the network. So what we also called as GCC, Giant Connected Component. So what we do is that we measure how many nodes are participating in a connected state, and when fragmentation occurs, how many nodes. Even if you take out one node, these are non-linear systems. The impact would not be 1 unit loss in functionality. Depending upon its spatial importance, we may have drastic change. So that is exactly what this SCF tries to map, which is total functionality at particular instant divided by what was the situation before the hazard.
So I might say then it's based on some network property.
It is a network property which is used almost ubiquitously in all robustness literature.
Okay. So the other question that I have is, see, when you are looking at the effect of one type of network, let us say, it could be the infrastructure network, and then there is another network that is driving it.
Mm-hmm.
So let's say you have floods, or the connected cities or regions and so on. So when you want to analyze these two networks that are different, the one is belonging to the climate system and other is belonging to the transportation system. How do you deal with the different time scales, right? I mean, because the information that you may have and the evolution of the dynamics obviously will be at different time scales. Can you throw some light on that?
No, I think so. This is excellent question, Arun. I mean, that how we deal. So there are both aspects here. In fact, not only temporal but also the spatial aspects.
Yes, exactly.
That is,
exactly. I was going to do that. Correct.
The resolution at which climate networks or things like that are operating. So I would say that that is why translation is not very clear just yet, that how we are going to translate the information that we obtain from climate networks to X and Y. But what these climate network essentially gives us, the kind of work that Arun, you and I, we are trying to do to understand this concurrence and so on, is
Right.
give us robust inputs into our physics-based models at least. That is, if extreme is onset there, what is the associated lag time by the time it would reach into central part of basin and start playing havoc. So we can first of all look into the statistics of what are these generative processes that has resulted in these extreme precipitation there and so on. So for example, in this particular study, although we were not imposing any network, but the causal event is exactly the same. It is precipitation extreme that resulted in flooding. It is precipitation extreme, the storm that moved from the Arabian Sea towards the inland of this basin that resulted in landslides and debris flow. What networks? So this is sort of reconstruction of an event. This happened, and then we are doing post-mortem of it.
Right.
But when we have the understanding of concurrency, that if an extreme sets up here, that what is the radial extent or what is the spatial extent, we can now really look into the associated statistics of those extremes. That are these events independent? Are they correlated, or they are causative in one way or another? I think that is the first entry point I see to interlink these heterogeneous spatio-temporal objects actually. In fact, we submitted a proposal a few years ago where we said that, first of all, let's not even worry about complexity. We know how to model infrastructures. We know how to model climate networks. But can we identify what is the credible resolution at which we can rely on the information that we are getting from climate networks? And to what resolution we should upscale our infrastructures so that impacts can be modeled realistically.
Right.
So I think that is still a very interesting and open question that we are still trying to find an answer to. That is why you would see that people have done excellent work in area of climate networks, excellent work in robustness. But interlinking these two, you would find limited evidence in literature and even in policy discourses.
Interesting. Yeah, and I think I probably have one final question. Generally, in the information that you have used, the data that you have used, are there any sources of uncertainty in the data? And if there are, how do you deal with those?
Yeah, so there are in fact a lot of uncertainties here. First, uncertainty itself comes from the precipitation data.
Okay.
That is, when we use this gridded data from IMD, it is going to have large variations, but each IMD grid is going to cover 25 kilometer by 25 kilometer.
Mm-hmm.
So what we do is that using the long-term data, we calculate the probabilities or of exceedances, what we also call as return level. Then we use those return levels and associated uncertainty from that statistical attribute to construct these uncertainty bounds, that what is the lower estimate, what is the upper bound of our estimates, and then where the medians are going to fall and so on. Similarly, we do the same exercise for our landslide modeling. So we try to look into the statistical aspect of this uncertainty analysis, but and also when we look into using climate models, for example, we try to address both irreducible uncertainty that comes from sensitivity to initial conditions, where we run our forcing models with multiple initial conditions, 30 to 50 in some case, and then we get all equally likelihood scenarios. We don't associate probabilities with them because we don't know which initial condition is more reliable versus the other. And the rounding of that we are doing is 10 to the power minus 14 at some time step. And that results in entirely different or diverging dynamics. And then we also look into the anthropogenic uncertainties that comes from the different RCPs, that is concentration pathways, different modeling groups, which essentially try to encapsulate different kind of physics in their climate model. And then we take the precipitation, temperature outputs from these models and try to understand what is the spectrum that we would have around our estimates of return levels and so on. In fact, I've not shown that work, but that was one of the core part of my thesis, is that how we can use information from multiple initial condition ensembles of nonlinear dynamical systems to reduce the so-called irreducible uncertainty.
Interesting. Okay. Great. So thanks. That was certainly a very detailed answer. And I see that there is some, there are no questions in the chat window. And I don't see any raised hands as well. Of course, I understand it's a bit late in the evening. People must be hungry, and I think if we don't close, we can see some extreme events happening. So thanks a lot. That was a very, very good talk. Fantastic. And Chayan or Sunetra, over to you. Any closing words for the day?
No, Arun, I think, it was a very eventful day. We had a fantastic presentation, starting with yours. So let's close today and let's come back tomorrow at 3 o'clock.
Yes. So Udit, please join us, Satyam, and all the other speakers. Please do join us whenever you can, tomorrow and then the day after. And we have an interesting line of talks, right?
Yeah,
and of
let's have good interactions tomorrow also. Like today.
Yes. Absolutely. So thanks a lot, and see you all tomorrow at 3 o'clock.
Yes. Bye, everyone.
See you. Good night.
Yeah, good night.
Yeah. Bye, Udit.